Well, let me check if I'm live or not. Okay, check it out. Okay, it's live. So let's start with this. So today, we're going to understand how JavaScript. Let me set it up with this also. The audio. Let me fix the audio first. It's fine. Okay. So today we're going to understand these four topics. And the reason for this is to understand how does JavaScript, gets executed in the backend. How does JavaScript code actually is executed in the browser and also in the server, sorry, in the Node.js. And why does it behave differently in browser, and why does it have different, runtime elements in the browser and also different runtime elements in the Node.js runtime when you're running in the server. So first of all, these are the four topics we are going to discuss: the event loop mechanism with call stack, and why promises beat set timer in the queue. You will understand these to when we talk about the call stack, and how V8 reads and compile your code, and what is JIT. These two are to make you understand how your code sometimes get slow in certain environments. I mean, not the usual small application code, but when you're working in a big code bases, then. So first of all, to understand this, you need to have some context about threading. So there are two types of languages: single-threaded versus multi-threaded languages. And the single-threaded language, which is JavaScript. And why does it act like a multi-threaded language? Okay, I'm fumbling it a little badly. And why does JavaScript act like a multi-threaded language? So first of all, let's understand what single-threaded means. It means that your CPU core, the engine or the runtime, can execute one task at a time. For example, you have multiple functions. Okay, let's say this function 1, function 2, function 3. So in a single threaded language, the function first will execute first and then second and third in a sequence. And no two functions will be executed at a single time, as if the function 1 is not executed, it will not move to second one. And if the second function is not executed, it will not move to the third one. So the single threaded means that the task 1 will be first. The sequence in which the tasks are aligned in the call stack, for example, this is your file. You have a certain function of API user, function API, token calls, and function API response. What it means that first the API user function will be executed, and then API token calls, and then the API response. It cannot be, as the user function is being executed, the API token calls is also simultaneously being executed. It will not happen in a single threaded language, but it will happen in multi-threaded. So why do we even use single threaded? I mean, there are a lot of benefits of this also. So this is single threaded language. As the threads execute tasks sequentially, each task must finish before the next one begins. It is also easy, simple to design, no risk condition, and it is also easy to write the code for this single threaded language. And it is easy to because you don't have to, like Java. Java is difficult to debug rather than JavaScript or Python. So the single threaded language or Python, JavaScript, Ruby, and multi-threaded means that the CPU can have multiple parallel tasks running at the same time when executing multiple tasks. For example, it has 3 tasks running all this at the same time. But you also have to, um code for these conditions. When you're coding, when you're programming in the multi-threaded languages. So, and also have to, it's a bit difficult to debug, but it is faster, and better CPU usage, non-blocking. So when you're handling a little bit complex code bases, like Java, Spring Boot, you will, code in these manners. Now that you have understood what single-threaded versus multi-threaded means, let's move on to the actual concept that we're going to discuss today. And before I explain anything, let me show you something that is going to help you understand what this means. So this is a code. Okay, I'm going to run it now. Okay, let me remove this one first. Wait a minute. Okay, now. Oh, this is not needed. This was the code. Okay, now. Okay, you would have thought that when the code is executed, code will be executed. It will be in the execution order of 1, 2, and 3. But in reality, the code executed is 1, 3, 2. So why was 3 executed before the set timer 2? This is the reason we're going to understand the call stack. Why does this phenomena happen? So let's understand this. This example was necessary as it will reveal how entire JavaScript runtime works, and also it will be important to understand before we get into the async and promises of JavaScript. So here's where we'll start. So JavaScript is single-threaded, as we have understood that it has only one single call stack. And first of all, in the manner the call stack follows a last in, first out order. So this is the last in example. Okay, this is the last in element, and the elements are actually like this. For example, this was the first, and then comes a second function that is main, and then comes a third function that is square, and then comes a fourth function that is multiply. The first function to get executed will be multiply. So this was the understanding of what last and first order is. So what this means is, as this is also means that it is single threaded. Okay, don't move. That it is single threaded. That means that it can only do one thing at a time. One call stack, one thread of execution, completely synchronous. So in simple terms, it means that you can only execute one function at a time. And when you will call a function, for example, any function, it will, for example, there are multiple functions in this line, and whatever function is called, it will be placed onto the call stack, and then the next and the next and the next. For the example, this is the last function in the file, and it will sit on the top of it. But when you visualize it as this is how it works, then you will wonder that this will create a massive problem. Imagine you're on a web page and you will click a button that needs to fetch data from a server. And if JavaScript has some other function before fetching the data from the server, your web page will not load properly. It will get stuck there until the previous function gets executed. For example, no matter how much time it takes. So it will freeze completely. You will not be able to scroll, can't click anything else. The entire browser tab will become unresponsive. Because why? Because the call stack will get blocked. As one function will, for example, one function this, whatever this is. Okay. This is API fetch function. Until this function gets executed, these functions will not be able to execute. So you will be waiting for a network response. Nothing will happen. No rendering, no user interaction, no nothing. This is obviously terrible. So how does JavaScript handles this? How does this whole structure work so that even if your call stack is fetching some API data from somewhere, the other function gets executed? Let me show you how all these pieces fit together, how the V8 engine, which is this memory heap and call stack, how the V8 engine, that's where your JavaScript will actually runs. And it has two main parts. The call stack, this is where your code will get executed last and first out when you call a function. It will get pushed to the top when it finishes and pops up. And your code runs here, one function at a time. And memory heap is the memory where your all variables, objects, and data will live. It is unstructured at the time. So, and also your browser, the JavaScript in your browser, the browser provides you more than that V8. It will provide DOM events to show animation. It will provide set timer so that a function can be executed after a certain amount of time, and it will have a fetch function promises and and a request frame animation, which is not included here for the animation and stuff. And these are not part of JavaScript. These web APIs, the browser node, it is not part of JavaScript, but it is a separate system that the browser provides for the extra things that the JavaScript enables us to do in the browser. And this is where the actual magic happens, so that the browser is able to continuously and consistently perform those actions. Now, let's understand the whole flow. For example, you have a set timer function. This is a set timer function, set timeout function. When you will run this function, it will get pushed on the call stack, at the first time, and it has a set timer function of time, time 1 second after, 3 seconds. Okay, to execute it after 3 seconds. When you will call this function, it will get pushed onto the call stack, and then JavaScript will not execute the timer itself. It will just register it with the web API, and this is okay. It is near web API set timer. It will register it here, and the call stack will be popped immediately off from here. It is popped from here to the set timer web API. It will move it here, and the other function will keep on running. Meanwhile, the web API will handle the actual waiting in the background. Your call stack is free. You're not blocked. The browser can keep doing other things while the timer is counts down. But now, what will happen when the timer finishes? How will the callback comes back? You can't just throw it back to the call stack and have it executed. It might interrupt something important that is being executed at that moment. Now there are two other queues, two elements that help it execute properly. The first one is microtask queue, and the second one is task callback queue. The microtask queue is the most priority seeking element, and that whatever is pushed onto this microtask queue will be executed before this callback queue. So it has priority. The microtask queue has priority over the callback queue. The timeout promises, set timeout, set intervals will be executed in the callback queue, and the promises, queue, microtask, motion mutations, whatever it is, the API mutations will be executed in the microtask queue. Now, when the set timeout function is pushed to the web API will push to the callback queue, and then when all the other functions are executed and the timeout of 3 seconds is passed, then it will push that into the event loop, and it will check that if the call stack is empty at that moment, it will push that set timeout back to the call stack, and it will get executed. But now you will be asking that what is the function of this microtask queue? That what is the purpose of this other queue? This queue handles the more priority functions. For example, if you have a promise here, or if you have a set timer here, set timer here. So which function do you think will be executed first? Promise, set timer. Don't focus on these two, because if these are simple console log or um, the functions that do not need web APIs, that if they are variables, they will be executed before any of these two. But these two, we have to understand that these two have a difference. For example, if the promises is pushed to the web API, it will push it to the microtask queue, and then the set timer will push to the callback queue. So here we have okay, okay, it's not. This is promise, and it pushed here. So these are two functions. The promise is pushed to microtask queue because it is a priority function. These are, previously defined. It is also defined that this function will be a microtask queue priority function, and set timer is a callback queue function. So before the set timer is executed, the promise will be executed before the set timer, and it will be pushed to the event loop. And then if the call stack is empty, it will move it here, and only then after it is executed, the promise is executed, and then the set timer is pushed to the event loop, and then back again to the call stack. This is how this whole async call works. This is how the JavaScript, which is single-threaded, how this whole JavaScript weird engine, the web APIs, and these two microtask queues and callback queue and event loop makes it possible to JavaScript to act asynchronous, to enable it to perform other functions while the APIs are waiting for a data fetch. This is the JavaScript runtime execution flow. Now let's move on to the Google's V8 engine. This looks complicated, but it's pretty simple. Let me show you the notes. Okay, I made these notes so that you also able to read. So the V8 engine is by Google, which is written in C++. So the main job of V8 is to take your human readable code, that is JavaScript, and convert it into machine code, as it's not entirely interpreted language or a compiled language JavaScript, because it uses both of these to get the best of both worlds. So it doesn't really interpret JavaScript line one by one like as old scripting language. It compiles, but in a very efficient manner, a very clever manner. So it has three main phases in which it is done: the parsing, compilation, and execution. The JIT, which is often asked in the interviews. So first of all, you have a file, your script.js file, which is the source code. And then when the V8 engine gets it, first of all, it parses it. It try to understand it. And then first of all, it tokenizes the source code. For example, you have this source code. Let me show you here. You have this source code. First of all, it will parse, make it into small parts. Okay. It will tokenize that what is a variable, and it will divide the variables and objects differently, and it will have a system ready to parse the JavaScript code. And after the code is being is understood, in small meaningful units, keywords, operators, identifiers, it builds a it builds a tree of that code that is tokenized, the parts of the code that is breaked into meaningful units. After the code is broken into multiple meaningful units, it is made into a tree. For example, you can see this code, okay, this is the code. It will define what the body contains. For example, this, where does it start? It will make a tree so that it can understand the shape of the data structure of your code. So it's a way of understanding it's a way of VA to understand how the code is connected together before executing the code. And then the code is interpreted, compiled, and then interpreted. After the, a very efficient tokenized and breaking of code, and then making a easy to understand tree, it is compiled and then interpreted and converted into a bytecode that is executed immediately. This is simple steps. You have understood that this is how the code is executed. Now, where is this GIT? So this is a very clever part of a V8, that it's nearly neither interpreted or compiled. It uses both, as if the code is being, if a part of the code, for example, a function or any block of code is being used repeatedly in your application or your script, it will try to use a turbofan, which first of all will be identified by a hot code. If the code is run off very often, it will come into the category of hot code, and then a turbofan will be assigned to turbofan. And when the core code is detected that this code is repeatedly executed or is used, then turbofan will optimize it and then it will emit a machine code which is execute fast native execution. And for example, you have a part that is executed and optimized for a turbofan, but you change that code, a function, you change something in that code, for example, a function, a variable, and then it will fall back to bytecode. It will not try to optimize it because something has changed in the code. So from the hot reload and turbofan, it will move back to bytecode and then it will be executed. It will de-optimize because a change of a variable. So the V8 also has heap to store the variables or objects, and a call stack to execute these code functions better, and the garbage collector for whatever variable is not being used or that is not part of any function. You will use the garbage collector, and cache to remember how the earlier code was executed. So this was the Google's V8 and call stack. That is